So now I would like to introduce the second talk from Dr. Sarah Neuwirth. She is a recipient of the Lovelace PRACE Award from this year. She is the deputy group leader in the modular supercomputing and quantum computing group at Goethe University of Frankfurt. She obtained her PhD in 2018 in computer science from Heidelberg University, also in Germany. And she was honored with the Zonta Science Award 2019 for her outstanding dissertation. So her research focuses on parallel file systems, modular supercomputing, performance, engineering, high-performance networks, benchmarking, parallel I/O, and communication protocols. And as I heard, she will become now a professor in Mainz, I guess, so soon. So the floor is yours, and congratulations.
Okay, let me check. Can you all? Okay, it's on. Well, thank you for the introductions, and it's a great honor to be here. And as you just heard, my research focus has been spreading out in multiple directions in the last couple of years. So instead of talking about what probably got me to the point on receiving this great honor, I would like to dive into a bit of what I'm currently focusing on, and maybe even hopefully get you to think about how to engage performance engineering and researchers in my domain, because I need input from people that are using HPC resources. I'm on the systems side. So I sometimes do not understand what you do if you're approaching it as a research scientist from your domain. But before I get started, I wanted to acknowledge this is a great honor to receive this award this time, and I also think it's important to still keep raising awareness for diversity and inclusivity. So thank you to PRACE and one of the first programmers in the world, Lovelace, to have contributed to this great award. So let's get into performance engineering. Oftentimes, if you're focusing on your research, and we've just seen a great presentation about how science is done and how you use HPC resources to advance science, especially now that we have exascale computing, sometimes performance engineering is one thing people do not want to think about too much because it can be a hassle. It is still important though. Why? Well, it helps drive science because if you use performance engineering as a tool to advance your science in a sense of helping make your simulations, your applications, your workloads perform better, whatever better means, we might get there, hopefully by the end of the talk. It'll make your life easier in the sense of you might reduce your runtime, you might use resources more efficiently, you might help reducing the cost for future systems because we might be able to use them in a better way, but you also might help reducing the carbon footprint because sustainability has been a buzzword that needs to be addressed, especially now that climate change has become very obvious. So this is just a very generic slide introducing performance engineering, but what I wanted to point out is on the right side, it is a cycle that has been continuously researched and worked with over the past decades, and it is still very recent and of interest to the community. Let me head into why. Observation 1, we've seen a recent shift towards a more diverse workload environment on HPC systems. So when I started as a PhD student, and it hasn't been that long ago, we mostly focused on very traditional HPC, which was super easy, and please don't come at me for saying easy, but it was still easy to somewhat predict how it would behave. It was dominated by very bulk synchronous I/O, for example. You would have heavy read and write phases, checkpointing, your very traditional simulation workloads. But now, in the last couple of years, we have advanced towards emerging workloads that are now encompassing so many different forms of workloads, including artificial intelligence, big data analytics that have been, especially in bioinformatics, quite of importance in the last couple of years, but also deep learning, workflows, etc. And all of them have very different characteristics if you just look at I/O, but also if you look at the behavior as a complete system. And just to give you an idea, I put in a figure that showcases the classification of or more than 23,000 machine learning jobs that have been run on Summit, to give you an idea how many different science domains are actually using machine learning now as a tool to advance their science, but at the same time stressing systems tremendously. Another observation that is especially true in the European research community is the way HPC systems have been changing in the way we architect them. So for many, many years, we had the left side where we would call traditional HPC, where you have your compute system, you have a network that connects it to the center-wide file system, and then the center-wide file system consisting of servers. But Europe has been pursuing another path over the last couple of years, which is shown on the right side, where we divide the compute resources in smaller clusters, each with individual characteristics as expressed by the hardware they're using. Meaning that now we, for example, have a traditional cluster module with high-performance single-thread CPUs, but then you also have the booster module that is accumulating a lot of accelerators, for example, GPUs, and then other modules, such as data analytics modules that have a heterogeneous environment to serve big data analytics, but also in the future, and it's something the group that I'm working with right now is working on, integrating quantum computing modules. But then again, how would you even schedule jobs that are running on a traditional computer and quantum computing machines at the same time? Because then scheduling and timing becomes a whole new box. Again, performance engineering might be something that will be needed here. And then another thing that I stumbled across while actually preparing for today, which I thought was brilliant in the sense of that it was almost covering what I was intending to cover today. Just look at the date when Jeffrey Fetter gave this talk. I was barely an undergrad student back then in 2007, and he was exploring back then with the research community how the future of performance engineering would need to look like now that we were stepping into the petascale computing era. And you see, we had all these significant trends that are somewhat very similar to what we're observing nowadays. And we had still very similar approaches. We might have more advanced tools today. And then, main idea, we need to close those gaps between trends, performance observations, and the actual application and workload design. And all of this leads to performance engineering still being one of the necessary tools nowadays to help us use compute systems of the size of Summit or future compute systems that might be more complex, especially when we think about all the challenges that are ahead of us. So now, where are we with performance engineering solutions? When we look at performance engineering, we oftentimes have very right away two different groups of people approaching basically the same problem, but with different intents. Users, and with users I mean research scientists using HPC resources to advance their science domains, oftentimes are mostly concerned with how can I use this system? Do I have to learn 50 new programming languages? Do I need to understand the architecture in the most specific details, or is it good enough if I have a very basic understanding? How does my application perform, especially if I have been running it on another system before and now move it to a newer system or a bigger system? So portability is one of the main concerns. Another big concern, reproducibility. Will similar simulations on different systems result, in similar results, or is it also basically tied down to the machine that we're using? And then systems on the other side, this includes system researchers, system engineers, everyone helping keep those systems running. They're more concerned with the actual operation, installation, configuration. They're interested into system monitoring, so if there is faulty behavior, it will be spotted very soon. So researchers then can again use the systems more efficiently. And another very important aspect is system security, so that your research is secure. So you see, we have a bit of, even though we all have performance engineering in mind, sometimes very different ideas of what should be achieved through performance engineering. And if you now move on to how we perform performance engineering, there's typically a very traditional cycle or cyclic approach to it, and I have put the approach on the right side, where you see you start with your oftentimes unoptimized workflow application, then you start to instrument it through different tools. You go then into the phase where you actually collect data so you can analyze what is going on with your application or workflow on this specific machine, to then use this data to represent it in a more human approachable manner, meaning instead of 1 million lines of log information, you might want to plot it in a way or represent it or condense it into something that we can actually comprehend before you go into the actual phase where you evaluate those outputs and then either find ways to optimize the code and apply these optimizations, or you come up with the conclusion, yes, it does not perform as we want to, but we do not understand yet why. And depending how satisfied you are with this cycle, you would continue this cycle over and over again. And I put down a lot of different tools from the European, but also the US research community that are being used to help drive these, performance engineering cycles, if you want to say so. But performance engineering is more than just applying those tools. We have more that we can use. One approach that is very popular, performance modeling. And there we could spend another couple of hours just exploring how performance modeling can be done. There are statistical models, heuristic-based models, mathematical models, machine learning-based models, so many different ones. The most important thing is that here we are focusing on resources and try to understand how the software and hardware is interacting with each other. No matter what model we're using, we're always trying to derive and get an estimate for the performance, for example, for a given application. And one very naive approach, naive in the sense of that it is very human readable, we can look at it and maybe even get an idea about what's going on, is the naive roofline model that had been used to quantify compute-bound versus memory-bound applications, where you basically look at the gigaflops being achieved versus the memory being consumed. And it is very easy to understand. You can basically get a rich point by putting it into a cathesis system here and derive from there how your application is basically performing in comparison to the theoretical bandwidth and the actual peak performance observed by a system. Then how, once you have done all these modeling and cycle, you're applying the performance optimization. There is, again, the cyclic approach. I have walked you somewhat through it already, but recently there has been at least work that users do not have to do this all by themselves, to work together with, user groups, user support groups at different sites. So intensely, there have been a lot of advances to automate this process, make it automatic, make it user-friendlier, if you want to say so. And this is actually driving a discussion where last week I was attending HPC, and it was really interesting to see that there was even someone who said, no, we cannot make it too easy for users, because if they don't have to work for the performance will degrade eventually, because they don't even have to think about whether what they're applying makes sense or not anymore. And I thought that was very interesting, especially now that we have all these cyclic approaches that are trying to do automatically in the background, collect all the information we need, then extract the information we need, and then maybe give hints or even apply optimizations based on these hints. But where does this lead to? If we use all these tools, and there are so many different ones, which is why I understand why users are sometimes like, how should I even know which tool is the right one for the system that I'm using and what am I even looking at? There's so many colorful pictures in a sense of that. I don't even know what I need to look at to understand what's going wrong. Is two specific areas that I think need to be addressed in a different way in the future. That's visualization, basically the way information is being reduced and presented to researchers, human beings, people that are trying to understand what's actually going on. And then the other thing is we need a constant user engagement and probably also vendor engagement in order to further, improve applications, but also at the same time help that we do not need to do these extensive performance engineering cycles over and over again after the application has been running, but more like to get them engaged before they're even putting their system, application to a given system. And this is something where I see a lot of potential that hasn't been worked on as much as we should have. And the interesting thing is I've been talking to a lot of people from the performance engineering community in the last couple of months. And all of them are basically saying, yes, we're reinventing the wheel, but we're not really integrating the user in this cycle of reinventing the wheel. But where does this leave us? These are only the performance engineering solutions. So for the rest of this talk, I want to focus or maybe do some thought-provoking challenges and outlook discussion here in the sense of that, how might performance engineering need to change or what should be adapted on future systems so that performance engineering can be done in a more comprehensible way, user-approachable way, but at the same time keep track of what the system requirements are and the system needs. So one thing I think that is really interesting to explore, and that's something my group has been working on very recently, is multidimensional performance modeling. You see something as naive as the roofline model, and it's great to give you an idea how your application is performing in the sense of gigaflops and maybe how it is died down to the memory. But what about other dimensions? Performance is oftentimes, a result of multiple factors. Systems are shared. They have a shared network. I/O is essentially also using the shared network, but also the storage resources. You have the compute. You have the overlap of compute, communication, and I/O, and also factors such as software versions, compiler versions, so on, so on. And this is why I'm vouching for more advanced models in the sense of keep it in a way that users will still be able to get some information out of it, but at the same time incorporate more factors, such as, for example, trying to find a way to score network I/O and compute for your application. And yes, not every application will be on the compute side. Not every application will purely be on the network side. I get that. But just to give you a feeling, where do I stand with my application? What is the potential of the system that I'm actually using? Then the next thing, something that has been, can I say, eyesore for the research community in the systems domain, is that sometimes if you look at different conferences and the publications there, work is being done over and over again for the same problems. Because we do not have a way yet to categorize and keep the information. For example, different science domains, they all have some things that are very particular about their domain. They might have specific patterns in their application of how they're using resources, of how they're laying out the mathematics in the code. So why not find a way, a community-driven way, to establish a community database to categorize systems versus your actual science domains versus patterns used by those domains, to get a first step towards understanding what different science domains need in the sense of performance engineering, instead of taking the same application on 5 different systems and doing the same work over and over again, being more efficient on the long run. And this is also something that I'm particularly interested in, on how you can use all these different tools that are existing, integrate them with each other, so especially users do not have to hassle with how to even get to work them together and how to extract the information I'm interested in. But then also how to apply this information for different use cases, meaning optimization, yes, big thing, we need that, but also, for example, anomaly detection in the sense of finding faulty hardware in the system to help the running and operating the system more efficiently. Then again, helping the researchers using these systems running their science, because if the system's unavailable because the network's down or a link is not working or a hard drive doesn't work anymore, that doesn't help anyone at all. And then also basically preserving this information in the sense of that it is accessible to the community and not just to me or the specific researcher, but to everyone, so you have a starting point instead of starting all at the beginning of the cycle again. And then, of course, other important things, artificial intelligence and large language models, and this has triggered a huge discussion last week, at least at the conference. At some point, because I was part of a panel on performance engineering and whether user experience or system is more important, and we came to the result that you can't just say one of them is more important than the other, was why don't you just throw ChatGPT at, HPC systems and be like, here, these are the parameters you need to run your code with. This is the best MPI run with the file system settings, and this is how you need to set the compile flags, and there we go. And the result was that we might be able to do it, but just not yet. Why? Tools such as ChatGPT, they need a tremendous amount of, training data sets. And at this point, we do not have collected the right information yet to train them in a way that people that have been focusing on performance engineering for a long time are able to, so that basically the prediction models or the artificial intelligence would be able to give you this set. It's not available yet. Maybe we do not even understand the questions that we need to ask yet in order to get the information we're looking for. But then the other question that has been addressed, or was a hot topic, was how far should we go with digital twins? And here digital twins does not mean to have a digital twin of your actual science experiment or the research that you're doing in your lab. More like, for example, digital twins of ourselves. Should a digital twin know me better than I know myself? So as you can see, a lot of potential there for performance engineering, HPC, but also a lot of different other questions. And to come to the end, because I'm running out of time, another challenge that has been somewhat disregarded for a long time by performance engineering, but also by other different domains in HPC, is the way we're optimizing systems. Up till now, we have been optimizing systems mostly for energy and system efficiency, meaning we're looking at runtime, we're looking at scheduling improvements, we're looking at integration of hardware to make systems more energy efficient. But something that has been disregarded needs now probably all the attention we can give it is sustainability. Meaning, how do we run the same HPC infrastructures as before, but in a sustainable manner to preserve energy, but at the same time also reduce the carbon footprint? And I had a couple of very interesting discussions, but something that I didn't even know existed, but someone pointed me to last week is this little map down there. This is actually a screenshot from yesterday evening, how the carbon footprint around the world looked like. And the question is, how can we use performance engineering to help, for example, with operating systems in a sense of that we make it more sustainable by, for example, moving applications between sites to areas where the carbon footprint is currently less than in other areas. And that's something that is not easy to do. And with this, I'm coming to the end of my talk. It's basically, are we reinventing the wheel? We might be, but we're addressing different questions this time. We still have significant trends, and you see I copied somewhat Jeffrey Fetter's slide layout, because we still have architectural complexity, but we now have also the rise of artificial intelligence. The application complexity has even further intensified, and sustainability now has become something that we really need to be concerned with. So overall, performance engineering will be a tool that is going to be needed, but in a holistic end-to-end manner where we try to preserve. And I hope that some of this has been thought-provoking to you, and hopefully you'll talk to your performance engineering person or community so that you can help us understand what we can do better in the future to help scientists drive research. And with that, thank you for your attention.
Thank you, Sarah, for this great talk. The floor is open for question. Yes, please.
Hello, I'm from the University of Edinburgh. Thank you for your very nice talk. I just wanted to comment on your last slide. Thank you for mentioning energy efficiency. I think it was the previous one, isn't it, where you had the map? But it's okay.
Huh.
It's okay. You had this map of the carbon intensity in the world.
It doesn't let me navigate.
Does not work?
No, it does not let me navigate anymore.
Okay.
It's okay. I can describe it in words. So, I mean, a lot of that is not computing. Okay, so there is a limited impact we have on that. I mean, it's a much bigger problem, and it's actually not completely clear what the carbon intensity purely coming from computing is. So that's something really interesting, and I think the HPC community should be worried about that. There is some element in software and computing that contribute a lot to this map that has nothing to do with us as well. Like, for example, there was a paper this year about what is the carbon intensity of rendering app on portable devices, and it's gigantic, much more than what we would be comfortable for, considering rendering ads doesn't contribute, you know, you could argue in a useful way to humanity. But anyway, for HPC specifically, I think the key thing is to give users in computing facilities the power of controlling their own energy efficiency. And that goes through something I've not seen being activated in a lot of systems, is controlling clocks of GPUs and CPU, controlling voltage controller when hardware add it, and push users to optimize the energy efficiency of their own code, because the problem is that it cannot be done from the whole facility point of view. It's a domain-specific problem. And even more, I would say that this question, benchmarking energy efficiency for HPC code, becomes more and more part of peer reviewing process or, you know, evaluation process of projects. So I think, you know, just a comment I wanted to make to the bullet point list you made here. Thank you.
Well, thank you for this great comment, and I totally agree. My intention was not to say that the HPC research is responsible purely for the carbon footprint, but it is something that was brought to my attention very recently, where I thought, we didn't think about this. We're purely thinking about how can we reduce runtime or, you know, utilization.
Yeah, just to add to that, I didn't mean to criticize the map. I just mean that this map is clear, but actually the part of computing of this map is something which is still being actively researched. And this is something we can contribute to, you know.
Absolutely. Thank you.
Lip.
Thank you for this brilliant presentation. At PRACE in past, we have organized work in the MOU between PRACE, CERN, the SCAE, the Square Kilometre Array Observatory, and GIANT. What about the efficiency of this giant workflow? And especially the one with regard to the SKO. If we want to look at the efficiency, the energy efficiency of the whole system, do you have already any hints or people who are able to encompass all these gigantic workflow?
I'm not sure I got that.
For instance, the Square Kilometre Array Observatory, which is in South Africa and Australia, and where we will have to use our HPC system to run the analysis of this data. Do you have already some hints how to have the global workflow taken into account in the efficiency of the system?
That is not a trivial question, actually, because if you're trying to think globally, the problem then becomes that we have country boundaries. So sometimes moving workloads or workflows from one, system side to another is not that easy. But it is an interesting question and something that we should think about, how you can operate distributed workflows more efficiently and at the same time have, keep an eye on energy efficiency, but also maybe reducing footprint. This will be something I'm going to focus on in the future because I cannot give you an answer right now. But great question, thank you.
We have time for one quick question.
Yeah. Thank you for the great talk. So the performance engineering cycle, measure, predict, optimize, looks really matching with what AI can do really good. And you mentioned that there is not enough information yet. The thing we know about ChatGPT and other large language models is that they train on a lot of data. So I would like to ask your thoughts on where can we get this data to kickstart the AI on performance engineering, and if we can turn this into a community effort?
That is probably going to be a community effort. So we spent, I think, 2 or 3 evenings last week really discussing this topic because, in theory, the tools that we have, for example, for like ChatGPT, they do have the tools that would be needed to you basically use it for performance engineering. The problem is the training sets that would be needed for that would need to be from multiple sites, and from what we understand so far is the data that has been collected does not include everything yet that would be needed, because oftentimes when you approach a system as a performance engineer, you do have, some background knowledge that you apply automatically that might have not been in the data that you had been collecting for training. So that's why I'm saying one of the first community efforts that will be needed is to ask the right questions so that we can then start collecting the data needed, so that we then have the training set from multiple different sites over, a longer time span, so that we can train those models. So this will be the first step, finding a way to ask the right question, and then just basically creating the data sets needed, meaning we need to collect them over a longer time, and then we can start using tools such as ChatGPT. But yeah, that's one of the things. It's not as, even though you would think, but that should be easy, right? When we started talking about it, it was not that straightforward.
Okay, thank you.
Okay, let's thank Sarah and Petrus again, and see you at the ceremony in the afternoon. Yeah.